The High Frontier, the complete deep dive. Welcome to Synapse Daily. In our first video, we gave you a glimpse of the 1975 Stanford Torus. We showed you the giant ring and the dream of space cities. But that was just the beginning. Today, we are going deeper. We are peeling back the layers of history and engineering. This journey covers 14 chapters of pure vision. We've broken it down into 3 massive segments. First, we travel back to 1969. We explore the secret blueprints, the physics of artificial gravity, and the lunar umbilicus that was meant to feed our construction. Second, we tackle the hard truth. We look at the 1970s energy crisis, the massive economic costs, and the political battles that nearly buried these plans forever. Finally, we enter the human heart. We examine the psychology of living in a small world, the stunning architecture of these lost Edens, and how 2026 technology is finally making this dream a reality. Forget everything you think you know about space stations. This isn't about visiting orbit. This is about moving the human race into the stars. This is the high frontier. Let's begin with Chapter 1. Chapter 1, The Summer of Radical Dreams, A World Beyond Earth. Welcome to Synapse Daily. Today, we are traveling back to a pivotal moment in the human story. The year is 1969. On the streets of America, the air is thick with the scent of change, protests, rock and roll, and the looming shadow of the Cold War. But while the world's eyes were glued to the grainy black and white footage of Neil Armstrong stepping onto the lunar dust, a different kind of revolution was being plotted in the quiet corridors of Stanford and Princeton. This was the summer of radical dreams. While the Apollo program was designed to prove we could visit the heavens, a group of scientists led by Dr. Gerard K. O'Neill began to ask if we could inhabit them. O'Neill, a high-energy physicist, didn't start this journey with a government grant. It started with a question to his freshman physics students: is the surface of a planet really the right place for an expanding technological civilization? To answer this, they had to deconstruct everything we knew about home. We are a species defined by gravity and atmosphere. For 200,000 years, we have lived at the bottom of a gravity well. O'Neill and his team realized that planets are actually quite inefficient. They are mostly dead weight. Only the surface is habitable, and getting off them requires massive amounts of energy. But in the space between worlds, there is infinite solar energy and millions of tons of material floating in the form of asteroids and lunar soil. In 1969, the Stanford studies officially began to map out the high frontier. They weren't looking for a new world across an ocean, they were looking to build a new world in the void. They envisioned a future where Earth would eventually be zoned as a garden, a protected historical park, while the heavy lifting of civilization, industry, energy production, and housing moved into the sky. It was the most audacious architectural plan in human history. Chapter 2, The Physics of the Spin and the Lunar Umbilicus. How do you manufacture a planet's worth of physics in a vacuum? You don't use magic, you use geometry and momentum. The Stanford Torus was the centerpiece of the 1970s studies. It was designed as a massive, hollow ring, 1,790 meters in diameter. But the beauty lay in its movement. The torus had to rotate. To simulate Earth's gravity, the ring would spin at exactly 1 revolution per minute. Why 1 revolution per minute? This is where the biology of the human inner ear meets the cold math of physics. If the rotation is too fast, say, 3 or 4 revolutions per minute, the Coriolis effect becomes nauseating. You would feel dizzy every time you turned your head. At 1 revolution per minute, the centrifugal force at the outer rim feels like a steady, comforting 1 g. You wouldn't feel like you were spinning, you would simply feel weight. But the engineering hurdle was the Massachusetts. To build a structure that can house 10,000 people and shield them from cosmic radiation, you need millions of tons of material. Launching that mass from Earth is a physical impossibility, the fuel costs alone would bankrupt a continent. The Stanford team turned to the moon. This birthed the concept of the mass driver. Imagine an electromagnetic railgun, 3 kilometers long, stretching across the lunar plains of Mare Tranquillitatis. This machine would accelerate buckets of lunar soil to lunar escape velocity, 2.4 kilometers per second. Because the moon has no atmosphere, these buckets would fly silently into space, heading toward a specific collection point in orbit called L2. From there, the mass catcher would collect the dust, and space smelters would refine it into aluminum, glass, and oxygen. This was the lunar umbilicus, a literal umbilical cord of raw material feeding the birth of a new celestial city. It was the first time humans viewed the moon not as a destination, but as a quarry. Chapter 3, An Internal Eden, the Architecture of Light and Shielding. If you were to stand inside the finished Stanford Torus, the first thing you would notice is the light. In space, the sun is a brutal, unfiltered searchlight. It is constant, blinding, and deadly. You cannot have windows in the traditional sense, because cosmic rays would shred your DNA within weeks. The Stanford solution was a masterpiece of passive architecture. They designed a series of non-rotating chevron mirrors. These are massive, angled slats that sit above the rotating ring. They catch the sunlight and bounce it through a series of reflections into the interior. This indirect lighting accomplishes two things. First, it filters out the lethal radiation, and second, it allows the colony to simulate a 24-hour day-night cycle. By simply tilting the external mirrors away, the colony managers could create a sunset. They could dim the lights for a cool, blue twilight. Inside the ring, the sky would be the other side of the colony, nearly 130 meters across. The ground would curve upward in a gentle slope. Because the interior was 130 meters wide and kilometers long, it allowed for real weather. The study suggested that the moisture from the trees and the people's breath would rise, condense, and eventually fall as a light mist or rain. They planned for the village not a series of high-rise blocks, but low-density, Mediterranean-style housing. They wanted the inhabitants to forget they were inside a machine. They used the lunar slag, the leftovers from the manufacturing process, as a 2-meter-thick outer shield to wrap around the entire donut. You were living in a bunker, but it looked like a Tuscan valley. This was the cosmic Eden, a perfect, engineered paradise where the temperature was always 72 degrees and the sun never set unless you wanted it to. Chapter 4, The Closed-Loop Soul, Sociology of the Cylinder. Building the colony was an engineering challenge, living in it was a sociological one. In a Stanford Torus, the environment is not something that just exists, it is something you must maintain. This is the ultimate closed-loop system. Every atom in the colony is accounted for. The oxygen is produced by the intensive agricultural modules. The water is recycled through complex filtration systems. If you over-fertilize your garden, the chemicals end up in the colony's drinking water within hours. This creates a radical shift in human psychology. The commons are no longer abstract. You are literally breathing your neighbor's exhaled carbon dioxide, which the trees then turn back into your oxygen. The Stanford researchers spent thousands of hours debating the social structure of these colonies. Would they be military outposts? Corporate towns? Or independent city-states? They favored the small-town model. By breaking the 10,000-person population into smaller clusters or villages, they hoped to prevent the alienation common in large Earth cities. But there was the nitrogen problem. While the moon has plenty of oxygen and metals, it is bone dry when it comes to nitrogen, the gas that makes up 78% of our air. To fill the torus, they would have to import nitrogen from Earth's atmosphere. This made the colony dependent on the home planet. This chapter of the study highlights the fragility of the frontier. One small leak, one biological pathogen, or one social uprising could end the experiment. To live in the torus was to accept a social contract of total interdependence. You weren't just a citizen, you were a component of a living, breathing biological machine. The researchers looked at the psychology of the curve, how living in a world that loops back on itself might change the way humans perceive time and space. Would we become more insular? Or would we finally realize that all of humanity is, in fact, living on a spaceship Earth, and the torus was just a smaller, more honest version of that reality? Chapter 4, The Biological Clockwork, Farming in the Void. We often think of space travel as a matter of fuel and metal. But the 1969 Stanford studies realized that for a colony to survive, it had to be a biological masterpiece. If the Stanford Torus was the body, the agricultural modules were the lungs and the stomach. To feed 10,000 people, you can't rely on supply ships from Earth. The cost would be astronomical. Instead, the researchers designed a tiered farming system that would make modern vertical farms look like primitive gardens. They planned for multiple agricultural rims where the environment was hyper-optimized. In these zones, the CO2 levels would be kept significantly higher than on Earth, around 1,500 parts per million. On Earth, that would make a human feel drowsy, but for a soybean or a stalk of corn, it is a turbocharge. Plants in the torus wouldn't just grow, they would explode with life. The researchers calculated that just 100 hectares of intensive farming could provide a total, balanced diet for the entire population. They planned 4 animal modules as well: rabbits, chickens, and fish, creatures that are efficient at converting feed to protein. But this created a terrifyingly tight feedback loop. Every chemical sprayed on a crop, every waste product from the livestock, had to be processed by the same water system the humans used. There was no way to throw things. In the 1975 summer study, they realized that the most important person in the colony wasn't the captain or the physicist, it was the ecological engineer. If the nitrogen-fixing bacteria in the soil died, the colony died. This realization forced a new kind of humility on the Stanford team. They weren't just building a city, they were trying to duplicate a 4-billion-year-old biosphere in a tin can. Chapter 5: The Geography of Nowhere, YL5. In the vast ocean of space between the Earth and the Moon, there are specific islands of stability. These are the Lagrangian points. The Stanford study didn't want to orbit the Earth or the Moon directly. Why? Because orbital mechanics are restless. If you are in low Earth orbit, you are constantly fighting the atmosphere. If you are in lunar orbit, the Moon's uneven gravity, the mascons, will eventually tug you out of position. The visionaries chose L5. Imagine a giant invisible triangle in space. The Earth is at one corner, the Moon is at another, and L5 is the third. At this point, the gravitational pull of the Earth and the Moon perfectly balance the centrifugal force of an object's motion. If you place a station at L5, it stays there. It requires almost no fuel to maintain its position. It is the most stable real estate in the solar system. But L5 offered more than just stability, it offered permanence. It was far enough away from Earth to be safe from planetary disasters, but close enough for a 3-day radio signal and supply run. By 1974, the L5 Society was formed. Their motto was L5 by 95. They saw this specific point in space as the gateway to the rest of the solar system. If you could build a colony at L5, you could build them anywhere. It was the high ground. The ultimate vantage point. Whoever controlled L5 controlled the flow of energy and materials between the Earth and the Moon. Chapter 6: The Energy Crisis and the Solar Power Pivot. To understand why NASA spent millions studying space colonies in the mid-70s, you have to look at the gas lines on Earth. The 1973 oil embargo had paralyzed the West. Energy was no longer cheap. Suddenly, the Stanford Torus wasn't just a cool idea, it was a potential solution to the global energy crisis. The study proposed the construction of solar power satellites, SPS. In space, the sun shines 24 hours a day, 365 days a year. There are no clouds, no night, and no atmosphere to block the rays. A solar panel in space is roughly 6 to 10 times more efficient than one on the ground. The plan was simple but gargantuan: use the Stanford Torus as a construction shack. The 10,000 residents would spend their days assembling massive solar arrays, kilometers wide, and then towing them into geostationary orbit. These satellites would beam energy down to Earth using low-density microwaves. On the ground, rectifying antennas, would catch the beams and convert them into electricity. It was clean, limitless, and carbon-free. The 1969 to 1975 reports argued that by building 10 of these colonies, we could retire every coal and oil plant on Earth. We would move the fire of civilization off the planet and just beam the light down. This was the economic engine of the high frontier. We weren't going to space to escape, we were going to space to save the Earth from itself. Chapter 7: The Mass Driver, the Electromagnetic Umbilical. If the L5 point was the location and the SPS was the paycheck, the mass driver was the muscle. You cannot build a 10 million ton colony with rockets. A Saturn V rocket is 90% fuel and 10% payload. To build a colony using Earth-launched rockets would require thousands of launches, destroying the ozone layer in the process. The Stanford team's solution was the ultimate low-cost transport, the mass driver. Based on the principles of a linear induction motor, the mass driver was a long track on the moon's surface. Small buckets containing lunar soil would be accelerated by powerful magnets. Because the moon has no air, the buckets could reach escape velocity 2.4 kilometers per second over a very short distance. At the end of the track, the bucket would decelerate, but the lunar soil inside would keep moving, flying off into space like a stone from a slingshot. These payloads would be aimed at a specific point in space, Lagrange point L2, where a giant mass catcher, essentially a massive net, would wait for them. This was a non-rocket space launch. It was powered by solar electricity. Once the mass driver was built, the cost of moving material into space dropped by 99%. You weren't burning millions of dollars of fuel, you were just throwing the moon at the colony. This is the technology that makes the Stanford studies still relevant today. It is the only way to build at scale. Chapter 8: The Price Tag of a New World. How much does a new world cost? In 1975 dollars, the Stanford team estimated the first colony would cost roughly $100 billion. To put that in perspective, the entire Apollo program cost about $25 billion. The Vietnam War cost over $110 billion. To the average politician, $100 billion for a donut in the sky sounded like insanity. But the Stanford researchers looked at the return on investment, ROI. They argued that once the first colony was established and the mass driver was operational, the second colony would be 80% cheaper. By the third or fourth colony, the system would be self-replicating. They envisioned a space manufacturing economy where the colonies would build more colonies. It was an exponential growth curve. They calculated that by the year 2010, there could be 100 million people living in orbit, and the income from the solar power satellites would have paid off the initial debt 10 times over. They weren't asking for a handout, they were proposing a business plan for the human race. But in the world of quarterly budgets and 4-year election cycles, exponential growth is a hard sell. Chapter 9: The Political Ice Age, The Death of the Dream. In the late 1970s, the dream hit a wall. That wall had a name: the Space Shuttle. NASA's budget was shrinking. The agency had to choose between the high frontier of O'Neill and the low Earth orbit of the shuttle. The shuttle was marketed as a space truck that would make travel routine. To fund it, NASA had to cannibalize almost every other long-term project. At the same time, the political climate turned hostile to grand visions. Senator William Proxmire, famous for his Golden Fleece Awards, which he gave to government projects he considered a waste of taxpayer money, targeted the space colony studies. He called the idea of NASA moving people into space a colossal waste of money and a nutty fantasy. By 1977, the funding for the Stanford studies dried up. The mass driver prototypes were moved to a basement at Princeton. The public's interest shifted from the future to the present. We entered the era of the disposable culture, and the idea of building a permanent, multi-generational home in the stars began to look like a relic of a more optimistic time. The blueprints were filed away in the NASA Ames archives, gathering dust, waiting for a generation that was brave enough or desperate enough to read them again. Chapter 10: The Solipsism Syndrome, The Psychology of a Small World. When you live in a world that is only 1.8 kilometers wide, your perspective on nature shifts. The Stanford researchers were deeply worried about what they called the solipsism syndrome. This is a psychological state where an individual begins to feel that everything around them is a dream, a fake, manufactured reality. In the Torus, every tree was planted by a human. Every breeze was generated by a fan. Every drop of rain was scheduled by a computer. On Earth, we are humbled by the vastness of the ocean or the height of a mountain. But in a colony, you are the master of everything you see. Does this make humans feel like gods, or does it make us feel like prisoners in a giant toy set? The study suggested that to combat this, the colony had to include randomness. They designed paths that weren't straight. They wanted gardens that grew a bit wild. They realized that for a human brain to remain healthy, it needs to be surprised. They also faced the surveillance trap. In a closed-loop system, everyone's resource use, their water, their power, their waste, is tracked. How do you maintain a sense of freedom and privacy when you are living inside a giant, life-sustaining machine? The Stanford reports argued that the village atmosphere was the only solution. People needed to feel like citizens, not crew members. Chapter 11: The Aesthetics of the High Frontier, 1970s Visionary Art. If you look at the original paintings by artists like Rick Gaitis and Don Davis, you see a future that looks surprisingly comfortable. It wasn't the sterile, white plastic aesthetic of 2001, A Space Odyssey. The Stanford Torus interior designs featured wood, stone, and brick. They wanted the architecture to be heavy to ground the inhabitants. The houses weren't futuristic pods, they looked like San Francisco row houses or Mediterranean villas. This was a deliberate choice. The visionaries knew that if space looked like a hospital, no one would want to stay. They also realized that the sky would be the most beautiful thing ever seen. Looking up, you wouldn't see a sun. You would see a shimmering, golden band of reflected light running down the center of the ring. You would see the weather forming in clouds drifting 100 meters above your head, mirroring the terrain below. This art of the torus proved that space could be beautiful. It proved that we didn't have to leave our humanity behind to leave our planet. Chapter 12: The 21st Century Awakening, the Billionaire O'Neillians. For 40 years, the Stanford studies were a niche interest for sci-fi fans. But in the 2010s and 2020s, something changed. The wealthiest people on Earth, men like Jeff Bezos, began to speak publicly about Gerard O'Neill. Bezos, who attended O'Neill's lectures, has made the Stanford Torus the North Star for his company, Blue Origin. Why? Because the physics are still perfect. While Elon Musk focuses on Mars, the O'Neillians argue that Mars is a mistake. Why move from one gravity well to another? Why live in a place with 0.38 g that will eventually degrade your muscles and bones? In 2026, we have things the 1969 team could only dream of: artificial intelligence to manage the closed-loop systems, 3D printing to build structures from lunar dust, and autonomous robotics to run the mass driver. The dreams of 1969 are finally meeting the technology of today. The cost of launching mass into orbit has dropped by 90% thanks to reusable rockets. The high frontier isn't a fantasy anymore, it's a business plan for the next century. Chapter 13: The Planet Trap, Why Planets Are for Beginners. This is the most controversial part of the Stanford philosophy, the idea that planets are the wrong place for a spacefaring species. Gerard O'Neill argued that a planet is like a cradle. It's where you start, but it's not where you belong. Think about it. Earth is a giant ball of rock. We only use a tiny sliver of its surface. The rest is inaccessible or too deep. In space, however, you can build as much land as you want. If we used the material in the asteroid belt alone, we could build enough Stanford Toruses to provide a living area 3,000 times larger than the surface of the Earth. We would have infinite room for growth, infinite energy, and we would never have to worry about a mass extinction event again. Moving into space colonies isn't about running away from Earth's problems, it's about graduating to the next level of existence. It's about becoming a Type 1 civilization on the Kardashev scale. Chapter 14: The Final Summary, The Legacy of the 1969 Visionaries. As we look back at the 1969 Stanford space colony studies, we see more than just blueprints. We see a testament to human optimism. At a time of war and social unrest, a group of scientists dared to look at the stars and see a home. They proved that we have the math. They proved that we have the materials. They proved that the only thing keeping us on Earth is our own lack of imagination. The Stanford Torus remains the most detailed, most scientifically sound vision for a human future in the cosmos. Will we finally build these islands in the sky? Or will we stay here, staring at the blueprints, until the sun goes down for the last time? The choice isn't up to NASA or the billionaires. It's up to the collective will of our species. This has been Synapse Daily. We hope this journey into the high frontier has changed the way you look at the sky tonight. Remember, the stars aren't just points of light. They are the neighbors of our future homes. Like this video if you learned something new. Comment your thoughts below and subscribe for more fascinating stories.